Hello everybody, welcome to Blue Marble Science. Did you guys know that gas molecules can get tired and just fall down? Well, Globebusters Bob seems to think so. Warning, severe facial and monitor damage alert is in effect. Get out those oven mitts, push the monitors back out of punching range, and let's light this dumpster fire and have some fun. Are you ready for some derp, Gladys? Well, let's get this show on the road.
Okay, here we go.
That are claiming that gases are not affected by a downward acceleration. While it is true that gas molecules, when you equalize from one tank to another, and you initially get that rush of gas molecules from a stored container into a vacuum, they will continue to bounce around and bounce and bounce and bounce all over the place.
Very good, Bob. That's exactly what happens. The gas molecules continue to bounce and bounce and bounce. And the reason they do that is covered by the fifth and sixth postulates of the kinetic molecular theory. Now, this comes from Purdue University, and postulate 5 tells us that collisions between gas particles, or collisions with the walls of the container or any other surface for that matter, are perfectly elastic. None of the energy is lost when a gas particle collides with something, whether that's another gas particle or a surface. And postulate 6 tells us that the average kinetic energy of a collection of gas particles is only dependent on the temperature, nothing else. So you're doing pretty good to this point. Unfortunately, I think Brian Leakey is about to interrupt you.
Eventually,
So Bob's bought into the bouncy ball theory of gas molecules. Now, it's already been demonstrated that you take the pressure adjacent to a vacuum tank, basically, and you remove the barrier, then it equalizes instantly. The bromine gas rushes in to the pressureless tank, and the only thing that changes is entropy. There's no energy transfer. There's no temperature, no nothing. Okay, but according to Bob, I guess they just keep bouncing and bouncing, and eventually there is a change in energy. Okay, not initially when everything rushes in, but eventually it does change. Come on, man.
You were doing fine, Brian, right up to that eventually part. But I'll tell you what, the come on, man was exactly what I was thinking.
even sometimes in the same place, right?
So Bob, does that, at the risk of sounding stupid, and I'm feeling pretty stupid at the moment.
No need to apologize, sir. You have every right to feel pretty stupid.
But does when you say everything goes down, do you mean gases as well inside this device?
Even gases will, yes, because if you have helium, and helium is the least dense gas we know, right?
Mm-hmm.
See, what did I tell you? You're perfectly justified.
But even helium has to be, if it's going to rise, it has to float up on something. Right? Well, if there's nothing to float up on, then what's it going to do? It's going to sit on the bottom.
So helium is going to sit on the bottom. Is that what I'm hearing? Helium is going to collect at the bottom of a vacuum chamber. Oh my God. Are you kidding me?
You've just been corrected by Brian Leakey, Bob. He doesn't know why you're wrong, but he knows you're wrong. You thought about changing your name?
Another parlor trick. Okay, allow me to demonstrate.
Everybody's seen this demonstration. A helium balloon floats because the volume of air it displaces weighs more than it does. If we lower the atmospheric pressure sufficiently, eventually the volume of air the balloon displaces weighs less than the balloon, and then the balloon no longer floats, it goes down. It's just that simple.
There we go, yeah. I was completely wrong. The helium does go down in a vacuum chamber. Or does it? Okay, the helium's lifting capacity has appeared to go down. But look at the helium. It is blowing.
Blowing is not the best way to think of this, Brian. The helium molecules are not blowing. They are moving randomly in all directions and exerting a pressure on the inside of the balloon. That's what's actually happening.
Every direction. The balloon is not sagging toward the bottom. I repeat, the helium is not sagging at the bottom. It will never go down to the bottom of a vacuum chamber. That is fucking retarded. The helium will blow in every direction. That balloon will expand. It's not pooling at the bottom. I understand they think that in their brains.
They who, Brian? I don't know anybody in their right mind that thinks the helium is going to end up in a puddle at the bottom of the chamber.
But look at the balloon. The balloon is expanding in every direction. Just because the balloon went down, the helium did not.
Oh, Bob, thank
It
goodness
is
you're here.
expanding
Hold on, I think they're
more
watching
and more
something.
Yeah, hold on a minute.
Can you
in
hear me?
Oh,
every
Hold on a minute.
direction.
Okay, is this a little better, my volume?
Yeah, perfect. Thanks, Bob.
much better.
Okay, cool. All right, here's the problem with Brian's demonstration. First of all, he's showing helium balloons, helium-filled balloons inside of a gas chamber. And so what's happening is, because of the fact that he's removing the external air component, the helium, being more buoyant, is expanding inside of the balloon because it's fighting to get outside because there is no pressure outside. But what I said was that the gas itself would settle to the bottom. So here's what's going to happen. So when those balloons burst, and you can't see this, and by the way, I made a mistake. It is actually hydrogen that is the lightest gas, not helium. Irrelevant though. It's whatever.
Yeah, you're gonna make it all 220? Yeah, 220, 221, whatever it takes.
So when those balloons burst, the hydrogen, or helium, excuse me, basically got rocket shipped all over the inside of that chamber, right? And they're bouncing around like a mofo, big time. And they're going to do that for quite some time because there is this elasticity to, the molecules themselves. But after a while, no, you can't. After a while, conservation of energy is going to take place, and that those gas molecules are going to slow down.
So which part of the sixth postulate is confusing you, Bob? The only way those gas molecules are going to slow down is if we cool them down.
Now, in order for the gas molecules to rise, they have to be buoyant in contrast to something else.
Bob is somehow trying to suggest that gas needs a more dense gas to float on top of in order for it to rise, which is absolute nonsense. Our atmosphere doesn't separate itself out into its constituents. If you put compressed air in a cylinder, it doesn't separate out into its constituents. That is just an absolutely ridiculous notion. Let's look at a little demonstration here. We have two gas columns. Each column has two chambers, and the chambers are separated at the moment by a barrier. The column on the left has bromine gas in the bottom chamber, and on the right the bromine is in the top chamber. When those barriers are removed, the two gases will mix, and you'll see that the only difference is the speed with which they mix. And that rate of diffusion is being influenced by Earth's gravity. In the column on the left, gravity is actually slowing down the rate of diffusion. In the column on the right, gravity helps the rate of diffusion. But over time, both columns will achieve a uniform mixture of all the gases that are in that column. Oxygen molecules will bounce off nitrogen molecules or bromine molecules or CO2 molecules, but no gas presents a barrier to any other gas. Gas molecules will continue moving randomly in all directions, bumping into other gas molecules or into the walls of the container until they fill the entire volume available to them. I don't know how Bob can get this that wrong.
Well, there is nothing else inside of that vacuum chamber. Therefore, gravity or the downward acceleration is going to take its toll on them, and they are going to sit on the bottom. How do I prove that? Well, look at Earth. Look at Earth, right? Why do we have a gas gradient on the Earth? The reason is because we have all these different gases, and and the downward acceleration is pulling them down. Therefore, at sea level, you have 14.7 psi. In some places that are below sea level, it actually goes up to about 18 or 19 psi. When you get up to 50,000 feet, it goes down considerably lower than that. There is a gradient there because the downward acceleration is pulling down on it, and that's exactly what is happening to that helium. And I guarantee you that after that helium exhausts and succumbs to entropy, essentially, those gas molecules are going to sit on the bottom of that gas chamber.
Are we understanding each other? You're an idiot!
And there's no energy loss,
Brian,
gain, anything.
Do you understand that I'm agreeing with you? I'm agreeing with you, but you cannot have perpetual motion of the gas molecules. Where are they getting the energy to do that? Eventually, they're going to run out of that kinetic energy and they're going to settle on the bottom.
What you just said is one of the most insanely idiotic things I have ever heard. At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought.
But when you initially discharge into that vacuum chamber, you bet they're flying around like a mofo everywhere. But like anything else, there is. I'm sorry. Say what?
That's slowing down. The condensation, isn't that the gas is slowing down and sort of becoming water?
Well, thanks for watching. I hope you enjoyed it. And remember, when we say how stupid can you be, that isn't a challenge. That's a question. Hey, don't forget to hit the like and subscribe buttons. Click the little bell if you want notifications. Shout out to all those nice folks that participate in the Patreon and all the good people who have helped so much with the Cavendish experiment. With that, I'll see you guys on the next one. I'm out of here.